Okay, so here we are back in Chapter 4. Remember we skipped 3 sections back when we were in Chapter 4. The idea being that Chapter 6 was going to be something that requires a lot of digesting. The earlier we get to Chapter 6, the better. And specifically, we can get there earlier by skipping anything that isn't in the prerequisite trail for Chapter 6, which isn't much. Right, but this optimization stuff is fits that bill. It's not in the prerequisite. You don't need to know optimization to do anything that is part of the process of getting Chapter 6. Okay, so now we return. Here's the big idea. Suppose we have a function. How do we find the maximum value of that function? Some function f, like this, and here's the domain. There's the target. Y'all saw some of this in single variable calculus classes, how to do optimization. Maxes and mins, right? And you take the derivative, set it equal to 0, don't forget to check the endpoints. And, that's pretty much how that works. Okay. Well, here we have a harder problem. Here we have a domain that's not just an interval. Now our domain is more than one-dimensional. So, for example, it might be some lumpy shape like this. What do you do? How do you deal with this? Well, there are a lot of analogies, but there are a lot of differences. Here's one of the analogies. You'll notice that some points in our domain are, let me say, we can talk about the boundary of the domain, and we can talk about the interior of the domain. So that's kind of just like it was in Calc 1. In Calc 1, the boundary was just the endpoints, right? And the interior was kind of the rest of the interval. Here's one of the big differences. Here, the boundary of the domain is not just 2 points. That makes a problem. In Calc 1, when the boundary is just 2 points, check them. There's just 2, right? It's not some Herculean task to say, check all the points on the boundary. There's only 2, and it's just not hard to plug them in and see. We don't need some sophisticated process for helping us eliminate as possible maxima the 2 points that are on the boundary. It's just not worth the effort. Okay. Here we have infinitely many points. We cannot just check them. So that's something we're going to have to deal with, and we'll deal with that soon. Okay, for the moment, though, we're going to start with the interior. How do we find critical points in the interior? In this section, I go to a bunch of trouble and define a bunch of things so I can precisely define what do I mean by the interior and what do I mean by the boundary. We're going to skip most of that. I think you know what I'm talking about when I say boundary. One little quibble, though, I will point out, you got to be careful in how sets are defined. In this set, for example, you will notice those points, by virtue of the solid line I'm using to indicate them, are part of the set in question. These points, notice I'm using a dotted line. That's how I'm indicating that those boundary points are actually not part of our set. I've kind of shaved off our set shaved off those points. So they're not part of the set at all. C is not part of the set. Okay. It is part of the boundary, but it's not part of the set itself. B is part of the set. Okay, so heads up. Sometimes a domain might be weird like this, in which case you got to think through what points are actually involved. Okay, so here's a graph, and so if your domain is like this, and again you have boundary in your domain, right? The function that you're trying to optimize looks like that, and so you got all these heights. You're trying to, in the graph context, we're trying to find the point on the graph that's highest on the graph, right? And there are different sort of points of interest to that question. So one point of interest would be a point like this. That's a point in the interior, and it gives us what we call a local maximum. It's a little mountaintop. It's not the highest mountaintop on planet Earth, right? It's still a mountaintop, and we call it a local max. Likewise, another one here. So we're going to talk about how to find local maxes, local critical points in general. Right? And that'll be the first thing we'll get to very, very soon here. But then notice there's another kind of maximum. There's also this point over here. That point on the graph comes from this point on the boundary. This is the highest value of the function. It's the highest point on the graph. And it's different. Right? It doesn't really look like a mountaintop. It's just the function's getting bigger all the way up to that point. It's not stopping. If the domain went further, the function would get higher, right? So there's something qualitatively different about that kind of a maximum. And there's going to be a different technique for how to find those. Okay, so we're going to have, again, two different techniques for finding candidates, possible maxes. We're going to have one set of rules for interior points, and then we're going to have a completely different technique for which there is no really good analogy in single variable calculus for how to find critical points on the boundary. We never really considered this question in Calc 1. On the Calc 1, the boundary is, again, it's just 2 points. It's not worth the trouble. Okay. So that's our situation, and here's the big strategy. I'll note quickly first that this is a process of elimination. Quick reminder, so it was in Calc 1. Let me remind you how that works. In Calc 1, suppose you have an interval like this, and on that interval you have a function. Let's see here. I guess I'll use black. It's fine. And suppose that the graph of the function looks like that. Again, I'm drawing a graph. That's the familiar picture for Calc 1 questions. How would I find the maxes? Well, you all know the rules. You take the derivative, you set it equal to 0, you check the endpoints also. Okay. So let's think through that process. What do I learn about this value of x down here? What do I learn about that point? By virtue of the fact that at that point the derivative is equal to 0, does that tell me that it's a maximum? No. Not at all. Right? This point here, this value of x, the derivative at that point is 0 also. The mere fact that the derivative is equal to 0, to the question of I'm looking for maxes specifically, the fact that the derivative is equal to 0 doesn't really tell you hardly anything. Right? This is a really important point to digest. A lot of students don't really get this and think, look, the way you find them is you take the derivative and set it equal to 0. That must mean that if you do that, then what you get are maxes. No, not even close. Right? In fact, a lot of students aware of this point perhaps might forget that there is yet another possibility, and that is the curve could look like something like that. And the derivative is equal to 0 at this point. Right? And does that tell me that, well, it's either one or the other. It's either a max or a min. No. Right? That's an inflection point. When you find a point where the derivative is equal to 0, very important thing, it means you don't know anything about what's happening at that point. That's what it means. Critical points are points where you don't know anything. Right? The terminology is kind of disingenuous in a way. We make it sound like there's something wrong with the point. Right? No, what's wrong is we're not very good at understanding it. Right? We don't know, so we're going to blame the point. Call it a critical point. It's not really quite fair. Okay. All right. So what we can do, where we learn, why do we bother taking the derivative and setting it equal to 0 if it doesn't help us learn anything? What it does is it's part of this process of elimination. If I have found the points where the derivative is 0, then other points, like let's take this point here, x, where the derivative is not 0. The derivative is not 0. I can absolutely draw a conclusion about that point. No question about it. Hands down, no question. that could not possibly be our maximum that we're looking for. I can eliminate that as a possible point because the function is in the process of increasing as I go in that direction, which I'm allowed to do. I'm right in the middle of the I can go whichever way I want, right? And as I go to the right there, the function's increasing. You can't be at the biggest point if the function's continuing to get bigger. Okay, so this is what we really know. That's not up for discussion. That is absolutely not the maximum. And then likewise, even if the derivative is negative, right? You take a point like this one, derivative is negative, right? Well, it's not, the function's not increasing as I go to the right, but if I were to go to the left, the function's increasing. This couldn't possibly be a maximum because the function can definitely get bigger. I just have to go to the left instead of the right. Okay, so this is the process of elimination perspective that I want to make sure everybody gets out of single variable optimization. We eliminate most of the points in the domain. That's the big idea. I eliminate practically every point in the domain. There's going to be a couple of points maybe here and there that I can't eliminate. I can't eliminate this point because it's on the boundary and I'm not allowed to go to the left. I can't say, hey, just go to the left and the function's increasing. I'm not allowed to go to the left. And I can't eliminate this right endpoint. That's why you have to always check the boundary points. I also can't eliminate that point perhaps because maybe the derivative is 0 there, and likewise there. But the vast majority of the points in the domain I can eliminate. Those are not what I'm looking for. And so that's why we take the derivative and set it equal to 0. The points that you get when you set the derivative equal to 0 are the points that I don't really know what's happening, but I've eliminated all the others. Okay, so this is the big picture strategy that we're going to take in optimization here as well. So here's the idea: if you're in the interior, well, let me talk about how it applies to the interior. In the interior, think about this. Suppose that there was some direction that you can go, and the directional derivative is non-zero. Function's increasing, or maybe you have to go backward. If this derivative is negative, then you have to go backwards. But if the point is that the function in one direction or the other is in the process of increasing, then that could not possibly be a local maximum, and we eliminate it from consideration. So how broadly does this apply? How many points can I eliminate? Most of them. This is a very powerful idea. Here's our formula for directional derivatives. How about this? Just go in the direction of the gradient vector. Right? We know the direction of the gradient vector. That's the direction the function's increasing the fastest. So wherever you are in the interior, just make the choice. I'm going to, from that point, start moving in the direction of the gradient vector. This formula here turns into this. And I see that I get a positive, asterisk, positive value for the directional derivative. The function's increasing. This couldn't possibly be a maximum. And in the vast majority of cases, then, most of these points I can therefore eliminate. Definitely not maxes. Yeah? Okay. All right, where can this argument go wrong? There's two ways that this argument can go wrong. Notice I require that the function be differentiable to make this argument, right? This formula here about gradients, that only works if the function's differentiable. If the function's not differentiable, this argument, this elimination argument, crashes and burns badly. It's not a thing, right? The gradient doesn't compute squat if the function's not differentiable. Okay. The other thing is, I was assuming that the gradient vector here was non-zero. If the gradient vector is 0, what I get here is directional derivative equals 0, and that doesn't eliminate anything either. Right? So these are the conditions here. I need the function to be differentiable with a non-zero gradient. And if either one of those fails, I don't know anything. And this gives us our formula for critical points in the interior. If the function fails to be differentiable, we don't know anything, critical point. If the gradient is the 0 vector, we don't know anything, critical point. Okay. All right, so let's see an example. Suppose I'm looking at this function right here. It's a function of two variables. It's defined everywhere, so our domain is all of R2. There's no boundary to worry about. We'll deal with boundaries later. How do I find critical points? And by the way, we'll worry about how to classify critical points momentarily, but right now, let's just find them. I find critical points by step 1. I got to ask, where does this function fail to be differentiable? I've got to find all of these points where f is not differentiable. There aren't any. It's a polynomial. Polynomials are differentiable everywhere. No problem. So, is this good news or bad news? I don't know how to decide on that. It's good news in the sense that, hey, this function's good. Right? It's bad news in the sense that I have not yet found any candidates, possible maxes, and I'm kind of looking for candidates for possible maxes. So again, is it good? Is it bad? That's subjective. That's up to you. Okay. Okay, but we did not get any critical points. Next thing, take this function, compute the gradient, set that gradient equal to the 0 vector, and solve. So in order for this gradient to be the 0 vector, I need for both individual components to be 0. I get some easy algebra. In this case, at least, easy algebra. This tells me x is plus or minus 1, which you see in the two solutions that I have here. And this, well, conveniently, that tells me y is just flat 0, and there's just no choice in the matter. So I have two options for x, only one option for y. Consider all possible combinations, of course, and in this case, there's only two critical points. So these are the points that I can't eliminate. Again, I don't know that they're maxes. I don't know that they're mins. I don't know that they're whatever other options there may be out there we haven't talked about yet. All I know is these are the only points left standing. I have eliminated all other points in the domain. No other points in the domain could possibly be a max. This is all that might be. Everybody on board? Okay. Right. Okay. There's another example there I'm going to let y'all take a look at. Now, a reminder, here's a picture of, this is what a max looks like. We haven't drawn this picture yet, but I bet you could envision this. This is what a min looks like, right? So this point is what we call a maximizer. This point down here is what we call a minimizer. Okay. How do we decide which one of these is it? Well, we have to recognize that there are more possibilities. And they're in single variable calculus. We have maxes, we have mins, and we have this third possibility, an inflection point. Okay. Well, are there inflection points in multiple variable functions? And yeah, and many other odd possibilities. We've got a lot of room to move around in our domain now. Functions can be doing weird things in different directions. There's some crazy kinds of critical points that are neither maxes nor mins, but all still kind of different from each other. And I just think it's fun to see a couple of examples of these kinds of things. So let's look at this thing here. This, at this point here, the function's got that value. The function is, in that direction, it's kind of a min if you're just looking along sort of the x direction. But if you're looking along the y direction, it's kind of a max. So which is this? And a lot of people would tell you this looks a lot like an inflection point. And I would say no, it's got certain characteristics in common with an inflection point, but they come from looking in different directions. There is no really sort of strong analog of this in single variable calculus. This is a new thing. So this is called a saddle point, by the way. Looks a lot like an old horse saddle, which I think dates the terminology. I think the much more relatable modern day terminology would be Pringle. There's a Pringle point. I think they should call these that in recognition of the fact that nobody rides horses anymore. right? Bet you everybody in this room has touched a Pringle more recently than a horse saddle. So anyway. But look, here, this is not the only other possibility. Here's this possibility. This is what I call a shoulder point, right? So if you look in the y direction, there's kind of an inflection sort of point happening, right? But if you look in the x direction, it's not an inflection in that direction. It's kind of a max in that direction. So this, again, there's no version of this in Calc 1. There's nothing really like this. And there's many other possibilities. Pringles and shoulders are not the only different sort of, non-max-min possibilities for critical points. There's bazillions of them. And I'm going to show you a picture of one that I think is interesting and also funny, and that is what they call the monkey saddle. This is a result of an easy Google search. They call it a monkey saddle. Now let's look at this picture over here. This picture, you can see the thing is, it slopes down in kind of 3 different directions. Well, a regular saddle, it sort of slopes down in 2 different directions because you got 2 legs and you need to have it slope down for your left leg and you need to have it slope down for your right leg. The monkey needs to have a 3rd sort of spot for his tail to slope down, right? And then somewhere down here, you scroll down, and someone has actually put a little monkey on a saddle, on a dog. I've forgotten where it is. Oh, yeah. Well, that's not. No, here it is. Yeah. So there's a real live monkey riding a dog. Anyway, but you'll see also there's a bunch of other weird shapes. Like, let's look at this one here. This one here, there's kind of 5. I don't know what you'd call that. That's a verging on like a spider saddle or something. It's an insect saddle, right? There's spots for lots of legs to hang down. This is a really different thing. This is not a Pringle. That's not a shoulder. It's really different. Okay, so it's fun. Okay, so there's a lot of different possibilities. We're not going to see techniques in this class for how to distinguish these from each other. We're going to call all of these saddle points because we're looking for maxes and mins, right? That's what we're really interested in. So we've got maxes, we've got mins, and we've got, neither, and therefore I don't care. That's going to be the level of our classification. Okay, so there's a long discussion as to how this works. The discussion that I just skipped over, by the way, is it's really not necessary for the course, but it's kind of interesting. But even it is also incomplete. So here is the punchline, though. I'm just going to cut to the quick. A full discussion of why this is true is pretty sophisticated. It requires some advanced linear algebra and just quite a bit of effort to come to this conclusion. So you're not responsible for why this theorem is true. Don't worry about it. But here's the result. This is kind of a second derivative test. It's not like the single variable second derivative test. The analogy breaks down pretty hard. So here's the punchline. You've got to look at the determinant of this matrix over here called the Hessian Matrix. The Hessian Matrix is made up of all of the second partials. All of the second partials of the function made into a matrix in sort of the obvious organization. You're going to compute all those second partials, arrange them as such. Okay. That matrix, if the determinant is positive, then there are 2 possibilities. It comes down to looking at the x second partial. If the x second partial is negative, you get a maximum. If it's positive, then you get a minimum. And these 2 parts of the second derivative test do look kind of familiar, right? That smacks vaguely of the single variable second derivative test. But it's very importantly different. This only applies if that determinant is positive. Right? And there was no such requirement, nothing analogous to that in Calc 1. If the determinant is negative, I don't care what that x second partial is. Doesn't matter at all. if that determinant is negative, you've got a saddle point of some sort. I don't know if it's a monkey saddle or a spider saddle or what, or a shoulder or a human saddle, whatever. I don't know, but it's not a max and it's not a min. Okay. Then you'll further notice that these conditions are not exhaustive. There's several possibilities that are not listed, like what if the determinant's 0? That's not on the list. Right? What if this second partial is 0? That's not on the list. Right? So if neither of these conditions is satisfied, then the test fails. You draw no conclusion. It's like you didn't even think of applying the test. You don't learn anything. And you just have to be sad. Actually, there's other techniques that you can apply, and we don't have time to. They're supplemental, but it's not something we can do in this course. Okay. All right, so that's the second derivative test. How are we doing? Is everybody on board? Okay. Let's see how this applies in an example. We've already found the critical points of that function. Here they are. Right? We did the algebra, took the gradient, set it equal to 0, solved, found these critical points. Now let's classify them. There's that Hessian matrix. That's this thing here. Here's the determinant of that Hessian matrix. That's just good old, plain old determinant. And let's start plugging in these points. We'll start with this one here. That point you plug in, its Hessian determinant is negative. And that means saddle point. A2 is a saddle point. Just following the rule of our second derivative test. Everybody see how that plugs in? Okay. All right. Now let's take this other critical point. Let's take that, plug it in, compute its Hessian determinant. Here it is. It's positive. Now, being positive, there's 2 remaining possibilities, right? I got to decide which one of these is it, and we decide on those possibilities by looking at the second partial with respect to x. That x second partial, you can see it right there in the Hessian matrix. Plug it in. Notice that it's positive. Being positive, we get a minimum. How are we doing? Everybody happy? All right. So that's how the second derivative test works. Sometimes the conditions fail. I'm going to let y'all read this one here. But I've got a function. You can compute the gradient. You can set it equal to 0. There's only one critical point. The critical point's at the origin. Plug into the Hessian. And your Hessian determinant's 0. So the test fails. Details for y'all, right? But the point is, this Hessian determinant being 0, none of these conditions are satisfied, and the test fails. Okay. All right, so let's move on now to boundaries. What do we do with boundaries? This is still a process of elimination. We're still going to be looking for ways to eliminate candidates. We're never going to have a technique that will just magically just go right to the maximum. That just, here it is, and this is the result of my algorithm, therefore it's the maximum. We're not going to have that. We're going to always kind of have to hack it down. Well, these are definitely not it, and then these are definitely not it, and so what's left over? Oh, well, then it must be this. Okay. All right. Okay. So here's some pictures of what our situation might look like. So, for example, maybe we're in 2 dimensions, and the boundary might be like this. Now, that's the boundary of this region here. Now, keep in mind, I'm no longer interested in the interior. Now we're just trying to talk about how to deal with the boundary. So we might be on this curve. And notice that curve, circumstances depending, that could be a level set of some function. And it's going to turn out this is going to be a really powerful tool in dealing with these boundaries. Figure out how to write your boundary as a level set of a function. We're going to assume that in this section. Okay, likewise, if you're in a 3-dimensional context, right? Here's your sort of interior, and now you've got a boundary. This time your boundary is a surface, right? Again, we're no longer interested in the interior. That surface could be viewed as a level set. Again, we're going to assume in this section that we have our surface written as a level set. Now, this surface, why are we interested in this surface again? Well, it's because it's the boundary of our solid, right? That was where we segued into this. But now let me point out, if our techniques are simply, if they're going to just depend on our surfaces being level sets, there's no law that says they have to actually be a boundary of anything. You could have a surface that's just like a, I don't know, like a paraboloid or something like that. You know, it could be just kind of, doesn't have to be the boundary of anything. So we're going to broaden our question a little bit to how would I find maxes? How would I find critical points? What can't I eliminate, right? If I'm looking at any sort of a level set. That's going to be what we're really going to talk about. Okay. Now, there's again, there's a two-dimensional version of this, right? And there's a three-dimensional version of this. They're pretty analogous, as it turns out. Just to keep it simple, I'm going to say, rather than talk about both, I'm just going to talk about one. I'm going to go ahead and do the R3 pictures because I think they're a little bit more persuasive, a little bit more general or something. I don't know. But the R2 argument is highly analogous. It's something that I encourage y'all to think through on your own also. Okay. All right. So we are looking at a level set. Flashback to earlier in chapter 4. Level sets are always perpendicular to gradients. So the gradient of this g function is perpendicular to the level set of the g function. Namely, the gradient of the g function is perpendicular to the surface I'm interested in. So that's the first big point. Okay. Oh, by the way, a little terminology. We're going to call this the constraint function. This function g is called the constraint function. I think it's a reasonable terminology, constraint, because that's the function that we use to describe which points are we interested in, which points are we restricted to, as opposed to which points do I not care about, they're not on my surface. So I'm going to be using this terminology, constraint function, throughout. And then just for distinction purposes, don't forget there's also the function I'm trying to maximize. I have to give that a name too, just to be general. I don't want to go around just calling it F all the time. What if I'm doing economics and it's P for profit? I might want to maximize profit, right? So it might not be called F, but what it always will be called is the objective function. Okay, so there's the terminology. Okay, so our constraint function, the gradient of our constraint function, by the way, I think this terminology is natural. This is called the constraint gradient. I'll be using that terminology a lot. The constraint gradient is always perpendicular to our surface. Okay. All right. So now that point aside, let's set that aside for a moment. Here's our constraint set. Again, we're stuck on this surface. We're not allowed to leave this surface. Suppose now my objective function has a gradient. I'm at some point on my surface. All right, let me do that in purple. At some point on my surface. And at that point, I'd like to know, hey, can I eliminate that as a possible maximum? I look at the objective gradient there, gradient of f. Suppose it looks like that. Can I eliminate this point A as a possible max? How would I eliminate this point as a possible max? Now look, in the previous section, our response to this was, okay, just go in the direction of the gradient. The function's increasing, end of story. And here's why this new question, the boundary question, the constrained question is harder. I'm not allowed to go in that direction. I'm stuck on this purple set. I'm not allowed to leave the constraint set. The gradient of f might be pointing off of the set. I can't do that. I can't eliminate A as possibly being what I'm looking for by way of an argument that suggests me doing something that I'm not allowed to do anyway. See, the argument just crashes and burns, fails miserably. Okay, so what we do, there's a simple way to resolve this. What we do is we simply say, okay, what vector tangent to the surface, what vector is there that, actually is a derivative vector of, some curve here in my constraint set? What vector is kind of closest to pointing in the direction of the gradient that, all else being equal, I wish I could go in that direction? And so I'm going to call that the projection. I think that's reasonable. This is the projection vector. And I'm not allowed to go that way, but I am allowed to go this way. I am perfectly allowed to go along this path that is entirely within my constraint surface. Yeah? Everybody good? And now let me just make the case now for what happens in this picture as I have it drawn here. If I go with that velocity along the curve that I just erased, if I'm going with that velocity, look, this is an acute angle. Cosine theta is positive. If I were to write down gradient f dot v, if I were to take that dot product there, I'm going to get a positive value. The function's increasing as I move in that direction. And as before, if the function is actually increasing as I move in that direction, then there's no way that this could possibly be a max. And that's the argument. That's our elimination argument. Like in the interior case, this is going to allow us to eliminate the vast majority of points in our domain. Algebraically how we do that, we'll get to that momentarily. Does everybody see the strategy? Right. So how can this argument fail? Well, this argument is based on looking at the formula for directional derivative. Like this, right? And if the function fails to be differentiable, this isn't true and our argument crashes and burns. So differentiability is a requirement for this argument. That's one of our vulnerabilities. It's got to be differentiable. Okay, how else are we vulnerable? Well, what if this picture is not representative? What if the gradient of f were perpendicular to the surface? If the gradient of f were perpendicular to the surface, then this projection down here would be nothing, and my argument fails. My v would be 0. I would be plugging in 0 into there, and I would not get that the function is increasing. I would get a derivative of 0, and that doesn't tell me anything. So the gradient of f being perpendicular to the surface, that's the other way, main way, that the argument crashes and burns. So we just pretty much have to watch out for those two things. Now I'm going to skip over some of the discussion and cut down to the punchline. Here are kind of those two conditions. Let's see here. Firstly, differentiability. If the function fails to be differentiable, critical point, right? Differentiability is important. If you don't have differentiability, you can't eliminate anything. Secondly, now I'm going to write this as gradient of f is a multiple of the gradient of g. That's not what I wrote here. What I wrote here was that the gradient of f be perpendicular to the surface. But don't forget, the gradient of g is always perpendicular to the surface. So if the gradient of f is perpendicular to the surface and the gradient of g is 2, then pretty much, I mean, there's an asterisk. I have to come back and talk about the asterisk. But generically, that would mean the gradient of f is a multiple of the gradient of g. Right? So this gradient of f being perpendicular to the surface is simultaneous, asterisk, with it being a multiple of the gradient of g. And thus this condition here. By the way, this scalar here, I don't know what that scalar is. It just needs to be some scalar, something that you multiply by the constraint gradient to get the objective gradient, and thus the name Lagrange multiplier theorem. That's called the multiplier. So, kind of neat. Right. Okay. All right. You may have noticed that I kind of glossed over this gradient of g equals 0 condition. This is also important. This is the most underappreciated condition on the list, right? Students have a good appreciation for the differentiability. You realize that, you've got a lot of experience of, functions with corners in them. You all saw a bunch of those in Calc 1 classes. The function's got a corner. Oh my gosh, that could totally be a minimum, and you've got a real strong picture of that. And we just talked about, the primary picture here, which is this, and you can see the multiplier formula. So why the gradient of g equals 0 is a problem is a little bit more subtle. And I'm going to come to this picture here real quick. So what would happen if the gradient of g is equal to 0? So let me just erase gradient of g from being what I had drawn there. If the gradient of g were 0, right, and this is our picture of the gradient of g, notice the gradient of f is now not a multiple of the gradient of g. It's not. There's nothing you can multiply by 0 to get not 0. And yet, this still could be a maximum, right? Look at our objective gradient is still perpendicular to the surface. This could be a maximum. I would not find it with the Lagrange condition, the multiplier condition. Right? So this is something you've got to worry about. When that constraint gradient is 0, that could be a maximum that you would just never notice looking only at that condition. So you've got to have this one as a condition as well. Okay, so you got 3 things to check. This is the new rules for how to find constrained, boundary most often, right? But constrained maxes. Look for points where the function fails to be differentiable. Look for points where the gradient of g is 0, not f, g, the constraint gradient. And then look for points where the gradient of f is a multiple of the gradient of g. Notice, by the way, while we're here, I'll point out that this includes the possibility that this might be 0, because that would be the consequence of that multiplier being 0. Right, so we didn't forget about gradient f equals 0. It's in there. Okay. All right, so let's get our hands dirty with an example. Here we go. We've got to look at this function right here. I want to find critical points of that function. My domain is this plane. Notice this plane, I do not have it currently written as function equals constant. But that would be easy to do. Right? I can rewrite this equation as that function equals 0. So I'm going to view this as my constraint function. And thereby it's real easy to compute this is our constraint gradient. How are we doing? Is everybody on board? Okay. All right. By the way, there's nothing magic about moving this 49 over to the other side. This constant over here does not have to be 0. I just did that for kind of aesthetics. If you wanted to scratch this off and have it equal to 49, that's also constant. That's fine. And notice it would give you the exact same constraint gradient. It doesn't matter. Suit yourself. Okay. All right, so we have a constraint function. We have a constraint gradient. Our objective function, the function we're trying to maximize, is there. Okay. All right, so let's look for issues. Differentiability. Right, the first condition, are there any points where the function fails to be differentiable? Nope. polynomial, differentiable everywhere, no problem. Okay. Next condition, the degeneracy condition. So recall the degeneracy condition. By the way, why it's called the degeneracy condition is reference to other issues that can arise that we're not going to talk about here, and it's kind of coincidental. Anyway, but just be aware of the name. I'm not going to be able to give you a good case for why we call it. It seems like a really rough term to label it degenerate. I mean, that's an insult, right? So it seems like strong language. It does deserve it, but for reasons that we can't talk about here. Okay. So the degeneracy condition. Here's the constraint gradient. Is this ever equal to 0? Are there any values of x, y, or z, or combinations of values of x, y, and z that would make this the 0 vector? Nope. Now that's an easy thing to check. It's easy to check. It's easy to write down. But it's important that you do. Keep in mind we're talking about a process of elimination, right? So if you don't do your full process of elimination and you look only at an incomplete set of critical points, you can't really draw any conclusions about them. Right? Just not fair. So it's very important, strategically speaking, on exams, on a question that's an optimization problem, the degeneracy condition will be worth a significant number of points, even if it's obviously not 0. You've got to say on here, never equal to 0. Or not equal 0, check mark. Fine, right? Be as brief as you like, but you've got to give me a clear indication of your reference to having checked that condition. Okay. All right. Right, so the last thing then is the Lagrange condition. So here's f. There's the gradient of f. Our gradient of g, well, we've already computed the gradient of g. There's that. So our Lagrange condition. There's our multiplier. Gradient of f is a multiple of the gradient of g. There's the algebra to sort of run away with one problem, one thing missing. Keep in mind, this is how I eliminate points that I'm worried about. What points am I worried about? I'm only interested in, keep in mind, I'm only interested in points that are actually on the constraint set. Points that are not on the constraint set, yeah, I'm not worried about them either. So we don't just solve just this algebra. You've got to add to that algebra, aka that algebra. You've got to add the original constraint condition in with your Lagrange conditions, and it's all of this together that you're interested in actually solving to find Lagrange critical points. Right? Because this doesn't amount to a hill of beans if it results in a point that's not even on your constraint set in the first place. Who cares? You want to find the point on this surface that maximizes a certain function. I don't care about points that are over here, right? So don't forget to put that condition in there. Okay, and now begins the sort of the ugly side of the process. That is, how do you solve this equation, this system of equations? There's 4 variables, x, y, z, lambda. We don't know any of them. We have 4 equations and 4 unknowns. It's tedious. And by the way, this is one of the easy ones. This is linear. Right? What if we had nonlinear terms in there? Nonlinear systems are sometimes just downright intractable. I would say often downright intractable. And so this is a scary situation algebraically. Real quick side note, just so you know, this makes it very hard to write good Lagrange multiplier questions because I've got to make sure that the algebra isn't intractable, right? That wouldn't be fair. That's not at all reasonable. We've got to make sure there's a reasonable algebraic foot in the door for you to be able to do this algebra. I also don't want to make the algebra trivial, right? So So it's a delicate matter coming up with good Lagrange problems. There's really only a certain small number of good Lagrange problems, and I pretty much put the vast majority of them in the exercises of this section. So if you are careful with and do a good job on all of the algebra for all of the Lagrange problems in section 4.12, you'll be in pretty good shape for how to solve algebra that you're going to reasonably likely face in this course. So whatever that's worth. So how do you do it? What's the process? My favorite way is to do what we call eliminating one of the variables. So we're going to eliminate lambda. The way you eliminate a variable is you solve for it and then equate the results. I'm going to solve for lambda in all three of these equations. Not hard to do. Solve for lambda. Lambda is equal to these three different things, and therefore these three different things have to equal to each other. And notice that having set these things equal to each other, I can just kind of ignore lambda at this point. It's kind of gone. See what I'm saying? So we turn three equations involving x, y, z, and lambda into two equations involving just x, y, and z. We traded a variable for an equation. So anyway, all right, that's the idea. And it's all downhill from here. In these equations, notice that I can solve for y and z in terms of x. Once you know y and z in terms of x, well, y and z were part of our constraint equation. Keep in mind our constraint equation was 6x plus 3y plus 2z equals 49. Plug those into the constraint equation, and out comes x. Once you know x, that tells you y, and it tells you z. So this kind of broad stroke strategy is going to work pretty often. This eliminate the multiplier strategy. Okay. The details are, of course, different in every example. Always different, and sometimes a little more annoying and stuff like that. Okay, I want to show you another example. This is, I think, a really important example. So here we have our objective function. Here's what we're trying to optimize. There it is. And we have a constraint function, now again in the form, I'm going to give you an equation, but it's not hard to persuade yourself that this is the constraint function then, g. That's the function that you set equal to a constant, a la earlier discussion. Okay, so new f, new g, let's proceed. Is this function differentiable everywhere? Yes, differentiable. Okay, next, let's look at the constraint function. Here's our constraint gradient. Is this ever equal to 0? Uh-oh. Yeah. This can equal to 0. Now, there's a temptation to think here that we've found a degenerate critical point. Because, check it out, I can make this equal to 0. Right? All I have to do to make that equal to 0 is let x equal to 0 and y equal to 0 and z equal to 0, and yeah, that'll do it. So is this a degenerate critical point? And it turns out that even though you'd think, I mean, look, it is, the constraint gradient is 0. This is actually not a degenerate critical point, because this point is not on our constraint set. That's not even in the domain. Right? So, what you have here is the, I don't know, this is kind of like the whole, y'all know that phrase, the exception that proves the rule? It's kind of like that in a way, right? If you were going to find a degenerate critical point on that surface, there aren't any, because, look, this is what it would have to be, and that's not even it. That's kind of, I don't know, it's an analogy, whatever that's worth. But certainly, though, the punchline is, this would be the only possible degenerate critical point. It can't be because it's not on the set, so therefore there's no degenerate critical points. How are we doing? Everybody follow that algebra? Okay. Again, while I'm here, I cannot emphasize enough, it's very important to check the degeneracy condition just for, mathematical argument purposes. even in a case like this, well, what does it matter? We didn't find any degenerate critical points. Does it really matter then? And well, so it depends what your goal is. If your goal is to get the answer, and for that answer to be correct, then in this case it doesn't matter. But again, that's not what we do in this class, right? What we do in this class is understand arguments, legitimate mathematical arguments. And for your argument to be correct, you have to have considered all the options. If you fail to check your degeneracy condition, right, and then you go off and find your critical points and decide which one you think is your maximum, your argument is not complete. You might have forgotten to check. I mean, as far as you're aware, as far as your argument demonstrates, you might have forgotten to check, a point that could have ended up being the absolute maximum. Right? So that's what we do here, right? That's in this class, in Duke math classes. We're about ideas, valid mathematical reasoning, right? Deductive reasoning. So this is an essential part of that, deductive reasoning. So again, it's going to be worth significant points on test questions. Okay, let's see here. So no degenerate critical points, no differentiability critical points, and now we go off to doing the Lagrange business. Here's our Lagrange equations, right? The gradient of f was this. Gradient of g was this. There's that multiplier. This vector Lagrange equation is equivalent to these three equations, right? Don't forget the constraint as well, of course. Our constraint is this. And now let me show. We're about to step on a landmine. I want to make sure everybody sees the landmine before we step on it. And I'll go ahead and put the constraint equation here. It was x squared plus 4y squared plus 9z squared equals 36. So here's our four equations. It's not linear, so this, could be really hard. Here's the landmine. The landmine is to argue a little too fast and loose and to say, hey, check it out. This says lambda is equal to 1, but this says lambda is equal to a fourth. That's a contradiction. Pencils down, no Lagrange critical points, and you walk away feeling victorious. And it's completely wrong. It's dramatically wrong. This is dramatically wrong for a reason that is usually glossed over in high school algebra classes. And we can talk about how should high schools teach algebra. It depends on the students taking it, whether they're really going to need. But here we are in a much more advanced class. We need more algebraic sophistication than most high schools tend to worry about. Right? So we just committed a major algebra crime that, again, is often glossed over. And here it is. We just canceled the x's to solve for that lambda. You're not allowed to cancel things that might be 0. Right? So what we can really conclude from this is that lambda is equal to 1 or x is equal to 0. There's two possibilities, right? And likewise here, lambda is a fourth, or y is equal to 0. These are not in contradiction to each other at all. There is no contradiction. You've just got more algebra to work. You've got various cases you've got to deal with. That's what we've got. No contradiction. So let me show you how to deal with the in this case, and there's different approaches that you could take. I'm going to show you the one that I think is the easiest. You're of course allowed and encouraged to rip off this idea that I'm about to show you, just like I ripped it off from someone that showed me. Right? And the idea is to consider in these equations. First of all, let's assume x is not 0. I would like to start off with that as a consideration because that allows me to then go into that equation, and now I can cancel the x's, and that does allow me to get lambda equals 1. Now I still don't get a contradiction, right? I can't cancel the y's, I can't cancel the z's, there's no contradiction here, but at least I've got a lambda that I can then plug into there. And now what I get, if lambda is 1, 2y is 8y, okay, well that means that y is 0, and that means that z is 0. Everybody on board? So if x is not 0, y and z have to be 0, and then plugging all this information into the constraint, right, I can solve and see what x is. If y and z are both 0, solve for x. X turns out to be plus or minus 6. So it's a whole thing, right? But this process, of considering the possibility that x is not 0 results in these two critical points that I would have completely missed had I been too fast and loose with the algebra. And that's just one case, right? That's just the case where x is not 0. You could also consider y not 0. I'm going to leave the algebra for y'all. It's analogous to what we just talked about here, but if y is not 0, then you get two more critical points. And if z is not 0, again, algebra for y'all, it's analogous to what we just did, but if z is not 0, I get, again, two more critical points. We've got 6 critical points. Not no critical points, we have 6 of them. Okay, so I hope everybody sees how important this little algebraic landmine is. It's a big deal. Be careful with do not cancel zeros, right? Be careful with that. Consider the appropriate cases. Big deal. Okay. All right. Let's see how we're doing on time. Okay, well, we've got a couple of minutes here. The very last thing I want to say, I'm going to skip the two constraint section. This is something I usually don't get to anyway. It's not typically part of Standard Math 212. If you want to read this, you're very welcome to do it. All that happens is there's a harder picture to draw, and you get an extra term in your Lagrange condition, and you get some extra degeneracy conditions. You have 3 degeneracy conditions instead of just 1. But strategically, it's about the same. Here's an example that works through how the algebra plays out. But this is not something that y'all are responsible for in this course. What I do want to talk about real quick is how to actually turn critical points into global extrema. How do you find the absolute maximum? We've talked about how to find critical points. We've talked about how to classify interior critical points locally. But what if I want that absolute maximum? Biggest possible. Couple of things to say about that. First of all, you have to be sure that such a thing actually exists. It doesn't always. Here's a theorem that describes when an absolute maximum actually exists. Here's a couple of cases where they don't. Just for your consideration, right? This function here, that's got that kind of a gross discontinuity in it. There is no absolute maximizer. Here, where the set is open, there is no absolute maximizer. Here, where the set is not bounded, there is no absolute maximizer. So, in order to know that an absolute maximum actually exists, you need your objective to be continuous, and you need your domain to be closed and bounded. So these are 3 conditions that are not that hard to check, and just make sure to check that before you go off on a wild goose chase trying to find something that might not exist. Okay. That said, let's suppose we have a domain like this. We have a domain that has an interior. It's got a boundary. How am I going to find the absolute maximizer? And the argument is a real easy argument. It goes as follows. This absolute maximizer, if it were in the interior, it would have to be the biggest value of the function in the interior. Therefore, it would have to be a local maximum. Therefore, it would have to be a critical point in the interior. Okay, well, yeah, but what if it was over here on this edge? What if that's where the absolute maximizer is? Well, it would have to be the absolute maximum on that edge. It would have to be a critical point on that edge. Therefore, it would, well, I already said it would have to be a critical point on that edge. Right? So, you just go through and enumerate all the possibilities. Wherever that maximizer is, it would have to be a critical point on that corresponding piece of the domain. So we can find the absolute maximizer just by looking at all of the pieces of the domain separately. Look at that. 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 Consider all of these, what I call subdomains in here. Each one of these is a separate little optimization problem. Find all the critical points. Put them all into the same bucket. Whichever one makes the function the biggest. That's your absolute maximizer. So I think this is a no surprise answer. If you have a thing like this, you just apply the techniques we've already talked about to all of these individual situations. So, for example, how would I find a critical point? How would I find all the critical points on this edge? Well, there's a single constraint on this edge. On this edge, x is equal to 1. There's my constraint. That's my g of x comma y right there. And we have, you see here, a constraint function. Yeah, apply the Lagrange technique. Likewise for all of these pieces. So just go through each of the 5 pieces and look at all the critical points. Okay, what remains in this, that's the big idea of this section. It is mostly, from your point of view as students with the final exam to take, coming up real soon here, I want you to view this mostly as examples to look at. Several examples in here, right? And then some of them are a little tedious, right? And that's life. Optimization's annoying. And then also several exercises to practice with. Okay. I went 2 minutes over. Sorry about that. Okay, so we're done. See y'all later. And just while we're here, just as a reminder, final exam is Sunday. Don't forget, it's Sunday. It's 2 to 5 p.m. This is posted on the class schedule. It's also posted on the registrar's website. So see y'all then. And y'all are different, yeah.
Is it here?
Yes, it'll be here in this room. So I encourage you to be here a little early because early is better than late, right? Exam's going to start right at 2 o'clock. See you later.
Well, the homework's from today and yesterday be due during the day.
Right. So, no, so the homeworks that, for today and yesterday that would otherwise have been due, like, tomorrow, we're not meeting, so they're not going to be collected at all. They are still assigned. I'm going to put that in air quotes. They're assigned. You have to do them in the sense that they are, part of the course. They are, I'm assuming that you're going to do them in terms of how the final exam is going to be written, right? But you're not actually going to turn it in. They will not be graded. They're not part of your course grade. Okie dokie.